In this lesson we're going to talk about radiation. Now radiation is a thing that scares most people about nuclear power. It's invisible, it's deadly, it can make you horribly sick. So let's look into a bit more of the details about what it is, how deadly it really is, and what different levels are. Now one problem is the very word radiation, radioactive. Here's the dictionary definition of radiation: the emission of energy as electromagnetic waves or as moving subatomic particles, especially high energy particles which cause ionization. Now the emission of energy includes many things: radio waves, light, alpha particles, X-rays. So this is unfortunate because they're all called radiation. The radiation you're really worried about in nuclear reactors is ionizing radiation, and this is a distinction the media almost never makes. Ionizing radiation is radiation which has enough energy to knock electrons out of atoms. This means it can damage molecules by causing chemical reactions. It can go into the DNA in your body and rearrange it. And this in practice means there's got to be a certain pretty energetic radiation. For electromagnetic radiation, it means anything with mid-ultraviolet and higher frequencies. So that's mid-UV, hard UV, X-rays and gamma rays. Whereas soft ultraviolet, visible light, infrared and radio, it's radiation, but it's not ionizing radiation. The photons do not have enough energy to generally knock electrons out and cause chemical shifts. Now it's not a firm divide. There is some areas like in the soft ultraviolet where sometimes it can cause chemical reactions like sunburn, sometimes it can't, depends exactly what molecule is hit. But roughly speaking, this is a clear distinction. Ionizing radiation is enough energy to go into you and knock electrons out and therefore actually do chemical damage. It's usually measured with a Geiger counter, a scintillation counter or film or something like that. Now non-ionizing radiation, the light from the light bulbs that are shining on me as I film this, mobile phones, the radio emission when I talk on a mobile phone, it's sending signals out to the mobile phone tower. Now these do not cause chemical reactions. They do not have enough energy to knock electrons between different energy levels. Does that mean they're safe? Well, they can have an effect by heating. If you get enough of this radiation, like sunlight, ultraviolet light can give you cancer. Infrared or visible light can't give you skin cancer, but it could heat you up. You could die of heat exhaustion. A microwave oven could cook a potato. So if there's enough of this radiation, it can do damage, but it does damage by heating you up. So there's a debate about the safety of mobile phones, which is, sure, they're putting out radiation, radio waves, and some of that's going to heat up the part of your head, like your ear and your brain nearby. Is this heating enough to make a difference? Most people think no, because the heating produced by a mobile phone is like 0.01% of the natural heating caused by blood circulation and many other things. But that's the debate. But it's a quite different debate from ionizing radiation. Another thing to bear in mind for ionizing radiation is how far it penetrates into the body. And this varies depending what exact sort of radiation it is. Is it gamma rays, neutrons, alpha particles? Now, alpha particles are actually helium nuclei, 2 protons and 2 neutrons, and they are produced, for example, by plutonium, but they can only penetrate about 1/10 of a millimeter into your body. So you generally have a layer of dead skin on the outside that's 1/10 of a millimeter thick, so it never gets past that. So if I had a chunk of plutonium, I could pick it up and be perfectly safe, even though it's putting out lots of ionizing radiation. Plutonium is safe if you pick it up. What it's not safe is if it gets turned into dust and you breathe that into your lungs, because then the radiation can cause damage. With other forms of radiation like neutrons and gamma rays and fast-moving electrons can penetrate to various steps into the body. This is actually why they're useful for medical stuff. To deal with cancer, you want radiation that can penetrate in to get to the cancers. But it does mean they can do damage more widely over the body. Now, a crucial factor for any radiation is the half-life. If you have a pile of any radioactive substance like plutonium, it's got a certain probability per second of any given nucleus decaying, and it's completely random. It's a quantum mechanical random process, whether a particular one decays now or 1,000 years, but there's a certain probability, and 1 over the probability gives you a typical time. What this means is that when there's a lot of undecayed particles, you're going to get more decay, so the radioactivity is going to be high. But then as time goes on, there are going to be fewer and fewer radioactive particles left, and so it's going to go down. This graph is a graph of how much radiation is coming out. It's also a graph of how much of the decaying nuclide is actually there, because exponential curve, the gradient is the same as the value. So what this means is for any of these things, you're going to get the most radiation early on, and then it will drop off, and the time it takes to drop off by 50% is called the half-life. And this has all sorts of effects. Here, for example, is the amount of radioactivity you get from nuclear waste. So this is once you turn off your nuclear reactor and extract the waste, there's still that 3% of the heat from all the decaying elements that were produced. And there are different elements in there which have different half-lives. So to begin with, let's say 10 years after the nuclear waste. Well, here's a shorter period. So what you can see is the total amount of radioactivity drops off with time. And it drops at different numbers of years after it comes out because of different elements. So 10 years after discharge from a reactor, it's mostly cesium-137 that's causing the radioactivity, plus strontium-90. But those have half-lives that mean that by the time you're at 1,000 years, they've mostly gone away. Then it's other elements, other radionuclides take over. So as you can see, there's also different ones that crop up. You also get radioactive elements like the thorium that appears later because it's a decay product from some of the ones over here. So what this means is that typically nuclear waste is most radioactive to begin with, and the radioactivity steadily goes away. So for this particular composition, after a few thousand years, it's always going to be radioactive at some level because there are some very long-lived isotopes. When do you consider it should be safe? It's often considered to be safe when it's no more radioactive than the uranium ore that was mined in the first place, because there's uranium ore all over the world. And nobody thinks we've got to mine all the uranium ore and bury it somewhere else. It's just out there. So when our nuclear waste is no more reactive than natural uranium ore, that's considered to be safe. Of course, it's still not safe. There's still some radiation coming out. But you can see that even after 10 years, the radiation has dropped to 10 times and much more rapidly after that. So there's a lot of decrease in radioactivity because of the half-life. This is actually really important if there's ever a nuclear war. Now, when I was growing up in school in England in the 1970s, we had training classes about what to do if someone dropped an atomic bomb on London. And it was saying that there's going to be a lot of fallout radioactive material, so you should find a room with no windows in your house and put mattresses all around the walls and stay there, ideally for about 2 weeks. And the reason for this is that the nuclear fallout is mostly the radioactive material left over from the bomb itself, and a lot of these things have very short half-lives. The ones with very short half-lives give really bad radiation because they're breaking down fast. There's lots of alpha and beta and gamma particles, but it goes away quickly. And basically every time, if the time increases by a factor of 7, the dose drops by a factor of 10. So you see a dose in these arbitrary units of about 1,000 1 hour after the nuclear bomb exploded. It's by 2 hours after it's dropped in more than half. By 7 hours after it's dropped by 10 times. And so on, by 48 hours it's down another 10 times. So if there is a nuclear war, stay away from the fallout for as long as you can. The suggestion was often 2 days later you might be able to venture out for short times, and after 2 weeks most of the radiation is gone. So, radiation, dangerous, but usually goes away. The most dangerous ones are the ones that go away fastest.